Presentation now, and I will hand over to Managing Director of Phase Pacific, Frank Capillari. Frank.
Thanks, Bruno. Good morning, everyone, and welcome to this first day, Essential Field Testing's The Basics. My name, as Bruno has mentioned, is Frank Capillari. I'm the Managing Director at Phase Pacific. For those that don't know us and have not had an opportunity to meet us, we are a evaluated supplier of test solutions to the telco industry, and in particular we are a Keysight representative for the telco industry, and we have been supplying and supporting Telstra for some 17 years across all of Telstra's labs and within the field. Today we have two local specialists from Keysight who will take us through some of the basic principles of RF and over-the-air testing and how they apply in the world of 5G. Many of you may know Keysight, and for those that have been around as long as I have would be well aware that Keysight has a very strong heritage in test, initially HP as Hewlett-Packard and then as Agilent Technologies. Today, Keysight is the largest test and measurement company in the world with over 14,000 employees, multiple R&D sites, many subsidiaries such as Ixia, Anite, or Nemo, and more recently a company they've acquired called Eggplant. In Australia, they're headquartered in Melbourne, where they also have one of the largest calibration centres in this part of the world. So we're very fortunate to have Ashley Chan and Timothy Lee leading the session today, both very experienced application engineers with extensive RF knowledge. So today is an opportunity to listen to Timothy and to Ashley, for all of us to learn, ask questions, and hopefully it becomes a very useful and enjoyable session for you all. So Ashley, I think I will hand over to you to kick this off right now.
All right, thank you. Thanks, Frank. So good morning, everyone, and thanks for joining us today. My name is Ashley Chan, and together with me, I have Timothy Lee. We're both Keysight application engineers based of Keysight Australia, based in Mulgrave, Melbourne. Right, so without further ado, I'll just go ahead and start our session. So this is our agenda for today's fundamentals presentation. So we'll first go through a really quick overview, some terms and terminologies that we often use. You might already be very familiar with these terms, but just so that we're all on the same page, I'll just do a quick overview of that. And then I'll move on to OTA in general, the signal capture methods that are common to the labs or to what we do, as well as the types of analyzers we have. Then we'll, perhaps in the middle, take a little short break before we go into the low-level signal challenges, typically coming from the antenna and amplifiers that we use. Then we'll move on to OTA measurement in 5G and the EMF, electromagnetic field measurement that we have. Once this is over, I'll hand it over to Timothy, who will be doing a short demo on EMF measurement today. Right. All right, so this is the RF quick overview with some terms and terminologies. So when we talk about frequency, that's Hertz, the SI unit, which is 1 cycle per second. And then, of course, depending on the bandwidths, we have megahertz, gigahertz, terahertz, and so forth. So at DC levels, where we're talking about 0 hertz, we're often referring to direct current. And next we have millimeter wave. So this is where I think some people might just reference all of radio frequencies as just RF, but we do have a distinction between RF spectrum and the millimeter wave spectrum. So under millimeter wave, we typically cater that to frequencies in the 30 gigahertz to 300 gigahertz region. So anything below that would be considered under RF, which is defined mostly for radio communications and broadcasting. Then next we have the power terms that or units that we use. So watt is, of course, the SI unit of power equals to 1 joule per second. But in the RF world, we typically talk about dB, which is a ratio of the input and output powers. And sometimes it could be referenced to the voltage levels as well, depending on the measurements you do. dBm, when we talk about RF power, with reference to 1 milliwatt. dB microvolts is reference to 1 microvolt across 50 ohms, typically used for electrical field intensity measurements, or as I've mentioned earlier, the EMF measurements. And of course, phase is also related to power. So we talked about that every now and then. And it's a measure of how far the signal is offset from a reference point, each cycle spanning 360 degrees. Last but not least, it's the voltage standing wave ratio, which is a measure of the reflected power on a transmission line, otherwise also known as the matching. Okay. So I have here the Australian radio frequency spectrum. This is taken off ECMA. So depending on the frequencies that you work with, they're defined as very low frequencies, and which caters for things that are operating below 3 kilohertz. And as you can see, as you go higher in frequencies, the bands are really small, and each bands are allocated based on who's allowed to operate on those band waves. So for 5G FR2 signal, which is the millimeter wave signals, we are talking about 25 to 27.5 gigahertz. Anyone would like to take a guess? What's the quarter wavelength at 26 gigahertz? No? So the quarter wavelength at 26 gigahertz is only 3 millimeters. So you can imagine how tiny that is, and the complexity of the devices that will be operating at 5G FR2 bandwidths. So this little presentation would give you an idea of things that you have to consider when you're operating at those frequencies. Okay, so I'll move on to our OTA measurement, which is also known as over the air. What I have here is something common, or what will be more known to the field. So if we're talking about communications OTA measurements, you would have a base station, and you're trying to transmit signals across your users. And we're talking about how you have beamforming, where if there's a block of an apartment, and you need to make sure that signals can be routed through that. So just to simulate this in the field for us, we have here a handheld analyzer. So you could transmit. Of course, there's an optional amplifier that you could use. So, and based off the base station, you're going to detect that radio link. So it's going to transmit and then receive back on the other end of it. So this is what is more common in the field, but I'll just like to go on to some common test methods that are typically used in the labs, or what we would say controlled environment. So these are the three methods: direct far field, indirect far field, and near field scanning. So of course, before we can even talk about measurements in the field, there are manufacturers of devices, and they also need to run OTA measurements to characterize their DUTs, or device under test. So for direct far field, it's a simple design. It's done in a chamber. It's mature technology. It's been around for a while now. you have the flexibility of, characterizing antenna beam patterns, beam forming, and RF parameter tests, basically to check on how a device operates under a controlled environment. But of course, the cons to that is, it's subject to higher path loss, and it can get very large for smaller devices that operate at millimeter wave frequencies. It can also be really slow, and it's expensive. So next, then we have something called indirect far field, where the signals are bounced off and then received within, again, in the controlled environment, but instead of directing it directly to the dot, you get it bounced backward. So with that, you have what we would call a flexibility to do end-to-end performance signaling tests, besides the three other tests that is, similar to a direct far field method. But with this indirect far field method, you'll be able to do, it has a smaller footprint, so you'll be able to test larger devices. And there's also lower path loss and better accuracy. But similar to a direct far field method, it can be slow and expensive. So this is where the next method comes, which is near field scanning. So what we would do is just scan across an area instead of, directing it straight towards a dot. It's small and obviously lower costs to some extent for millimeter wave devices as well. So it works for passive antennas. You could do the characterization of those using near field scanning. But of course, because it's not doing a direct transmission test or receiver test, it will require high accurate positioners for millimeter wave. So if it was 3 millimeters at 26 gigahertz, so you can just imagine if you're a little offset, you're going to get inaccurate measurements. So it's not very applicable to modulated signals, just because of, you need it to be really accurate where you place the dot. And usually it's not used for transmission tests, particularly for active devices. And it can be also slow. So these are the three methods that you might just want to, have an idea of when they're talking about controlled environment OTA measurements. So next then is the types of analyzers we can use to do OTA measurements. We have on the left a signal analyzer, so it does RF analysis, and it can be done with wide bandwidths. We have up to about 1 gigahertz of analysis bandwidth. So it's great when you're trying to troubleshoot signals using a signal analyzer here. Otherwise, there's also oscilloscopes. So for people designing devices, they might use a oscilloscope because it does digital analysis, so you could see the whole, in time domain, the whole performance or characterization of that signal in particular, or a digitizer, which people use for reception channel measurement. And you could also do modulated signal transmission analysis. I would just like to add that all three of those can be used with Keysight's VSA, which is our vector signal analyzer software tool for demodulation analysis. But what you'll like to take note then is with scopes and digitizers, there's no limiter in it, so you could potentially zap the instrument if you're not sure of the signals that you're trying to measure. So in other words, if you kind of need to know what your signals are like when you're using a scope or a digitizer, whereas for a signal analyzer, you might have an idea of what your signal is, and you could proceed to do troubleshooting with it. So this is just a user interface of our VSA software. There's a link here if you're interested to look into it. The picture on the left is the digital demodulation graphs that we have. So as you can see, if you have an idea of what your signal looks like and demodulating it, you could actually detect that there's a interference signal at this point. And we could also use the VSA to just process the demodulation sections of your signal, like IQ data, your EVM and such. So those are the typical analyzers that we have. But of course, for the field, we would have the FieldFox, which is a compact analyzer that you could take out in the field, and it comes standard with the cable antenna mode. But it's also configurable to add, a signal analysis mode, a real-time signal analysis mode, and so forth. So we will be doing a demo in session 2 next week. You're all welcome, more than welcome to stay tuned to that. Okay. So I'll now move on to the OTA low-level signal challenges. Are we good here, or does anyone need a short break? I guess not. We get on time. Okay, so I'll move on to typical challenges that we're seeing with OTA measurements, and it's typically contributed by the antenna and amplifier. So we're just going to do a bit of back to basics. So I'm going to start off with antennas. As you would know, and if you're out in the field doing measurements, it's the interface between the electric signal to the air. So it's used either as a receiver or a transmitter or both. And it's also known as a transducer. So, this little animation here shows how the antenna works. So for any antennas, one of the most important parameters that you'll have to look into is the match or characteristic impedance of it, which typically is 50 ohms for standard networks, but there's also antennas that come in 75 ohms, typically used for radio TV tower networks because it has low loss transmission. So most designs are designed to 50 ohms just because it gives you the best of both worlds. You have good power and voltage, and that's part of the transmission network or transmission line theory that we're used to learning. Okay. So these are some common antennas that we have. So we have, your TV antenna, your aerial, and this one here is for your FM radio or airport tower for their communication networks. Then there's the horn antenna that we sometimes use. This would probably be something more familiar to the telecommunications network, your RF antennas. And this one here, which is a radar tower used in World War I. And when this station is powered up, you can actually hear the click across Russia, if I remember this correctly. So there are many different types of and forms of antennas. And they all come with a pattern. So you have the main lobe, the side lobes, and the back lobe. So just looking at this phase plot here, you would know that the direction of your antenna is critical because depending on the antenna type that you have, you might not be optimized, or the signals are not optimized if they're not directed at the right angles. So of course, this is just the formulas that we have that you could come up with the best elevation or optimal elevation and azimuth patterns. So we typically do use horn antennas for RF networks, at least for us in the test measurement side of things. So I'll just go through some antenna parameters that we normally use. So first is dBi, which is the gain comparison or the relative gain to an ideal isotropic antenna. It's usually a little higher than an isotropic antenna. So if the gain of an isotropic antenna is at 0, your antenna or whatever antenna that's being characterized would have a gain that's higher than the isotropic antenna here. Next, we will talk about beam width and directivity. So I talked about main lobe, side lobes. So just from this, you're directing it at a certain angle where you get maximum transmission or in the main lobe direction. But then there will also be, some side leakages coming or that will be picked up from the antenna. So from that, it's very obvious the direction of your antennas are important. So there are two kinds of antennas being characterized. It's directional versus a omnidirectional. So for a directional antenna, you're talking about a focus area. So your transmission or receiving end of it will be very focused to a certain area, whereas an omnidirectional is across in all directions. So you could relate that to, for those of you who have a Dyson fan, you could also choose to have it, the fan focus directly at you, or to have it in a diffuse mode, so it sweeps around. So similar concept, you get a targeted scan area. You'll have higher gain when it's at a focus point. So, and it's obviously easier to pinpoint to a certain direction, but because of that, it will most likely be a little more costly and there's limited coverage. In cases where you have a omnidirectional antenna, so it scans and monitors across, so it will only pick up lower gains. It's harder to pinpoint a target. But if you're out just to look for a problem area, this might be better because it's cheaper and it has a wider coverage. So just to sum it up, you'll definitely need to pick the right antenna for the right situation. Depending on if you're very sure of the target area, then you might go for a directional antenna. Or in the case where you're out troubleshooting or just looking for interference as the first step, you might use an omnidirectional antenna. So before this, I talk about matching, which is also VSWR. In other words, you'll have to make sure you select a good VSWR antenna, an antenna with good VSWR, so that you can, and within the correct frequency ranges, so that it's optimized for your measurement. So that's the first challenge coming from antennas. We now move on to amplifiers. So by default, amplifiers, you subject the input to a small signal or some level of power, it will amplify your output power, and the ratio of that is known as a gain. If you look at this little circuit here, it seems like it's not just an amplifier. So you would also need to design it for proper matching networks to ensure minimal loss of power going into the input of an amplifier and to maximize your output powers. So there are some parameters that influence your amplifier performance, and that's things to consider would be your frequency range, your gain levels, input-output impedance or the matching network that I talked about. There's also noise figure, output power, your saturated power or P1 dB, as well as operating temperatures. So the next few slides would be a little bit back to electronic basics of an amplifier. The first one here I have is gain. So as you can see, as we sweep across frequencies, the gain is not linear, or at least may not necessarily be flat across your frequency ranges as well as temperatures. So these are things you need to consider when you're selecting an amplifier. And of course, if you want an amplifier that works across a broad bandwidth or a broad range of frequencies, it will be costlier. So this is one area to take note. And then next would be, of course, your input-output impedance. So I talked about your 50 ohm match. So if you're operating within a certain region, you would definitely want to pick an amplifier that has a good input as well as output return losses. Again, there will be temperature effects, so you'll have to take this into account. Then we next have noise figure. I probably didn't mention too much about this before, but it's a measure of how noise could be added into your system. So if you have an amplifier with a high noise figure, it would introduce some noise into the amplification. So if you're trying to measure something that is very low level signal, this could be masked by the noise figure. So you wouldn't want to have an amplifier with a high noise figure. And also, just as a typical way of how amplifiers are designed, to improve the signal to noise ratio, lowering the receiver's antenna's noise figure is probably the easiest compared to trying to double up the antenna's transmitting gain or power. So that's the reason why noise figure is an important figure of merit that needs to be considered when you're picking an amplifier. Of course, then you'll need to check to what your maximum output powers are before it reaches saturation. So again, you'll have to know what sort of signals you're dealing with, or have an idea of what the signals are like before, so that you can pick the right amplifiers for your measurement. So this is the summary of how, based off what I talked about earlier on the amplifiers. So you definitely need to choose the right type of RF amplifiers based on the test conditions that you're looking at. And as I've shown earlier, the parameters that would affect your amplifiers are your frequency ranges, your gain, input-output impedance, your output power or saturation power, working temperature, and sizes. So I'm now into the OTA measurement in 5G. So we talked a lot about the challenges with OTA measurements. Here are the three main impacts or areas that you need to focus on when it comes to 5G OTA measurements. The first would be beam forming. Let me see if I can zoom in. So you need to, we talked about the antenna's beam forming angles, so that is critical. The antenna may not be, for every beam section, there'll be a focus point. So you need to know the beam index. So this is one area to be considerate about or to consider as you're dealing with 5G OTA measurements. Next is the handover between 5G and LTE. At least as far as we're aware at this moment, in non-standalone mode, it involves a handoff between 5G and LTE network. So you want to ensure a smooth handoff when the 5G LTE, the 5G signal is low and it has to switch back to an LTE network. This is an area that's critical and what you would want to be measuring. And lastly, it's interference. So of course, you don't want your antenna or the user's equipment to be detecting, signals that are not part of the network. So this is another area that we could use the field fox to do that kind of measurements. So again, some challenges that we are talking about. So this little bit here at the bottom is for your 4G or LTE network. So it's a headlamp. It covers a wider zone. But for 5G, it's a flashlight. So it's pretty much, depending on where you are, your signals could drop quite a bit, a fair bit. So that's what we would call a multipath that you need to check for. And then we have attenuations where if you're behind some trees or some buildings, this would also impact your 5G signals. So it's an area to be aware of. And there's something called the line of sight, where of course, if there's something blocking, you're not within line of sight, how bad is your signal, and if you are within line of sight, are your signals transmitting or receiving as expected? So these are things that that are challenges to OTA measurement, but with what we have, we're perhaps here to help with the OTA measurements. So I just like to bring this up as what we call it an atmospheric attenuation. And that's the reason why certain frequencies are selected for certain operation. If your base station is off a certain distance, it will be impacted by this atmospheric attenuation depending on where you are, as in the frequency range that you're operating at. So it's something to consider as you're doing these measurements. Okay, so that sums it up on OTA. I will switch to Tim now for the EMF measurement.
Okay, everyone. So before we move on, is there any questions along the way that we can help out? You can type in on the chat, or you can turn on your mic and can raise up the questions. Is there anyone? No questions? So far so good?
Yep, there's no questions in the chat box.
Okay.
Okay.
So yeah, I will move up to it. So I'm going to cover just a few slides, additional slides on the EMF measurements. So it's electromagnetic field measurements. So I'm sure you guys heard about this, especially in this COVID time, where you might have heard some conspiracy theories saying that the 5G is causing the COVID virus outbreak. And this is where we step in and say that it's not. And how do we do the measurements? So this is what I'm going to share with you. So you might have seen this spectrum out in Wikipedia, the ionizing and the non-ionizing region of the frequency. So definitely for 5G, we are ruling about this area, okay? And it's under non-ionizing. But as the base station for 5G increase in numbers in a small area because of the distance that the signal will be able to travel because of the frequency attenuation. So there's definitely more and more base stations popping up, and the concern about health and safety will be a primary concern for the residents around the area. So if you search around, yeah.
Sorry, Tim. You're not in presentation mode, full screen.
Okay, sorry.
Yeah, just sorry. Yep, all good now.
All good. All good. All
yep.
right. So yeah, continue. And this is the occupational exposure guideline by the international regulations. And according to it, anything at 2 gig to 3.5 gig, we should be within below 137 volts per meter. And how do we do the measurements on that? So I'm going to go over that in a while. So there are three common types of units that we do. We do measure during EMF measurements, and one of it is radio frequency. We use watt per area, which is W/M square, and then magnetic field, Gauss per area, and electrical field, volts per area. And all these units, we can set it in our field fox when we do the EMF measurements. And normally this EMF measurement is far field measurements. That's why we need to utilize all three axes, X, Y, and Z, to get an average reading. Having to say that, we have options to let user to select which axis they want in the field fox. I'm going to show you in the video in a while. So this is our solution for field fox with the triaxial antenna. I'm not sure whether you guys seen it before, and unfortunately the demo unit that we have right now has been returned to US. It was here in Australia for a month or so, back in June, July timeline. But if you're interested to try it again, to talk to us, we should be able to get one demo unit. Okay. And these are the measurements that we can conduct in field fox. On the left, let me turn on this one pointer. So on the left here, as you can see, this is a spectrum analysis mode in field fox, where we can do the channel power measurements in translating to the EMF unit. As you can see right now, it's dB microvolts per meter. So all these translations on this conversion is done automatically without the user doing anything. So user just need to select what type of unit they want to see, and user can just screenshot or save the data for reporting after that. And on this right side is the measurements for 5G signal. So we populate out the whole channel table so that it is user in creating report. As you can see right now, it's a dB microvolts per meter, which is in the EMF measurement. So the next, next, I'll close this one now. And okay, so this video I re-uploaded to YouTube. If you guys can check it later, and because we have some problem with the audio side of it, I'll just talk through over what I'm trying to do. Okay. So what you're seeing right now on the screen is the 5G signal. It's a real signal from Telstra base station for 5G. And this is in the RTSA mode. And now I'm trying to show you how it looks like, the Argos EMF antenna. It is very big. Just imagine it's a mega size lollipop candy. Yeah. So I'm going to attach it again. And this is a USB connector. So it will read the ROM built in the antenna for the antenna corrections. And it also power up the active circuit in the antenna. And this is an N-type connector that connects the antenna to field fox. So I'm going to try to retrieve the information from the ROM and go to system and try to retrieve that information, the corrections factor. So in detail, we can come up with a guide for you on how to use this. But for time being, just bear with us on what I was trying to do. So I managed to read back the corrections from the antenna via the USB. So yeah, what I'm trying to do right now is to measure the EMF, do the EMF measurement in spectrum analysis mode. And I'm going to channel measurements, just as I mentioned in the slide. And I try to measure 3.6 gig 5G NR signal from Telstra base station. And let me stop here for a while. So what I'm saying in the background is that if we compare this solution to the third-party solutions in the market, like those that you can get from eBay or even JCar, those detector, the EMF detector, normally is a wideband detector where you can't set the center frequency of interest. So they just capture everything that the detector is able to see and then report. It could be the right reporting frequency, it might not be the one that you want. So for Fieldfox, we are able to set the center frequency of interest, and then we should be able to measure what we want to see instead of getting everything that's in the environment. Yeah, so this is where I set the center frequency. I'm going to set the center frequency and set the channel power. (3.5 gig). Then the span is span I set it to 20 meg. So it's a channel power over a span of frequency. And because this is over the air measurements, the signal from the base station is very low. So what I do is I turn on the preamp, built-in preamp from Fieldfox, and I change the unit. Then I turn on the corrections. So this correction is from the readback from the USB. Then, so you can see the change when it's on and off. The corrections has been applied or it's not. Then I turn down the attenuations just to make sure that we are able to reach to very low level. But unfortunately, at the corner of that deck, I couldn't get anything out, so I have to move myself to another side of the house where I know the 5G signal is available. Yeah, before that, I also tried to do OTA measurements, but yeah, I can tell you that I couldn't get anything at the deck. So in detail, how to set up the 5G signal measurements, I also created another video where I went to one of the Telstra base stations on the 5G base stations in Knoxville. It's more detail on how I managed to capture all the information from SSB channel. You can refer that later. We're going to put that link in the slides that we're going to share with you guys later. So these are some of the steps that you have to do to measure the SSB signal, SSB channel information. So you set the center frequency, you set the auto detect, auto SSB detection. But again, it's because it's too far away, and that corner of my house doesn't have 5G signal. It's proven because I have a 5G S20, and there's no 5G signal available at this on this deck. So again, I turn on the preamp, I turn down the attenuations, and I still can't get anything. And I have to move to another part of the house. So here, I managed to capture the 5G signal center frequency to start with for SSB. And so I grab the center frequency from the auto detections, copy SSB frequency, and I go back to the OTA measurements. Yeah, turn off the auto detections. So these are the informations that we can get. Yep. And this is the default power measurements. It's not the EMF measurements. So I'm turning on the EMF measurements right now. So again, there are a few settings that you have to go through before you are able to turn on the EMF measurements. We can guide you through in detail when the time comes. Yeah. So EMF, and turn it on. And I'm going to zoom in to let you guys see the reading, which is similar to what we shown on the slide. Yeah, I'm still holding that antenna, the big lollipop. And this is a real reading, real life reading. I think the base station is about 2 kilometers away from my house. And well, it's still well within that spec. It's in microvolts, 37 microvolts per meter. And I'm going to change that the reading, the unit reading to dB volts per meter. And you're going to see that there's no reading because it's just way too low. Okay, I'm going to stop here. But of course you guys can go back to this YouTube link right after these presentations if you're interested, and then you know where to find us. If you have any questions regarding this 5G over the air measurements, or even any type of measurements that you're interested with, like interference, like how to do recording. So we do provide training, paid training from Keysight, and you just tell us what you plan to do, and we are able to customize that the training according to what you need. In detail, you can talk to Frank or Bruno about it, and then we should be able to align that part. So I finished my presentation on the video side. So any questions from the floor before I pass back to Frank? Any questions, anyone? No? Okay, I'll pass back to Frank. Frank, I'll make you a presenter just in case you have anything to show.
That's okay. Thanks, Timothy. Look, thank you very much, Ashley, Timothy, for that presentation. I do hope everyone's found it useful. Look, we certainly would like feedback from those attending to understand whether this covered the sorts of things you would like to hear from us. By all means, please provide some feedback. We can probably, what we will do is we'll send out a feedback form to those that have attended, just to get a gauge on whether we're sort of touching on the right areas for you. So you know, we know the importance of testing. We know the importance of testing in the field to resolve issues that impact conditions within delivering mobile services. So that's important. As we move into the 5G, move into millimetre wave, I think there's going to be a lot more new challenges for the field technicians to consider. We know the Australian regulatory bodies are putting some focus in this area. ACMA has recognised the need to have the right sort of tools. They've even gone out and purchased a number of field foxes for 5G spectrum monitoring and management, which was a competitive situation for us, where lots of vendors were evaluated and the field fox was selected as the tool of choice. So ACMA, as we understand, are planning to use the field fox to monitor both FR1 and FR2 spectrums. And some of the reasons they did choose the field fox revolve around the real-time spectrum analysis, its IP53 rating, the long battery life, the portability of the unit, the fact that it's fairly lightweight, and of course the integrated cable and antenna measurements. So we've mentioned this during the presentation. If there's a requirement and anyone's interested in having a closer look at any of the units at any time, we're more than happy to accommodate. So we'll send out a message with perhaps a feedback form and our contact details so that you can come back to us, and certainly we can do a follow-up with you. I'd like to remind you again, we do have a session next week on the 10th. This will go into some more complex test concepts and some further demonstrations, and we will also be joined by Keysight's Field Fox Worldwide Products Manager or Product Specialist. So the guy who's basically responsible for a lot of the features that go into the Field Fox, so he'll be joining next week as well to share some of his experiences in what customers are doing, and also an opportunity, I guess, to listen to some of the requirements from Telstra in particular. So if there are no last questions, I'll do a quick pause there just to see if anyone has any questions or any comments. I'll take that as a no. Okay, so look, thank you again all for attending, and I look forward to seeing most of you next week on day 2 of the sessions that we're offering. Thank you very much, everyone. Have a wonderful day.
Thank you.
Thank you.